All right, you guys, for number 7, it's pretty tough, I'm not gonna lie, but there is a very friendly sort of procedure associated to it. See, I feel like this is the kind of exercise that you have to know a lot of different things about it, but once you internalize it, it's actually pretty straightforward. So let's go piece by piece. On the one hand, they tell us to consider that this function equaling blah blah blah, this nasty thing over here, we have that z, okay, that symbol and the big C. So what this is telling you is that C pertains or is part of this subset of numbers that are complex. Okay, so all your Z variables are part of complex numbers, and complex numbers, you guys, is the same as if we would be talking about imaginary numbers. Okay, and so all your values of Z are your imaginary parts of your polynomial. On the other hand, you know that M pertains to all real values, which are da, 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 which are positive. So there's a small detail that might be very useful down the road. Okay, so basically your values for Z are the imaginary part of your polynomial, and your values for M are the real part of your polynomial. And with that information, they tell us given, okay, that's kind of huge. So given that Z minus 3i is a factor, that is another big word, of PZ, find the roots, that's another huge word, of PZ equaling 0. So guys, this is basically an exercise of finding the roots, okay? In that sense, the procedure is fairly straightforward, and it just gets kind of wild because we do have imaginary numbers going around. Now let's go piece by piece and really understand why I highlighted the words that I highlighted. So given that this is a factor, it's going to help me a lot to find the roots, okay? Now let's really get why. So on the one hand, what is a factor? Well, when you were factoring before entering the IB, before entering HL, when you were a little bit more innocent, you would factor stuff like, I don't know, x squared plus 4x plus 3, okay? And eventually you would have found out that the factors of 3, or really like 1 times 3, right, are 1 and 3. And so that means that 1 plus 3 gives 4, blah, 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 etc. Yeah, you would end up rewriting this, right, rewriting this quadratic as x plus 1 times x plus 3. And you would solve this by equaling it to 0 and saying, okay, so from here, I can say that because these two things are multiplying and this equals 0, either this on the left is 0 or this on the right is 0, or both. Because if you have a times b equals 0, you know for a fact that either a equals 0 or b equals 0. There's no other way for two numbers multiplying to equal 0. One of them gotta be 0, okay? And so with that in mind, technically the roots from here, you would say that, okay, so basically either x plus 1 equals 0 or x plus 3 equals 0, right? And so from there you have that x equals -1 or x equals -3. So this is fairly straightforward. I'm sure you've seen this. And why did I highlight the word factor? Because the factor ring that I just did is this guy along with, whoops, sorry, along with this guy. Those are your two factors, okay? And so basically they're handing you, like to your face, some of the roots. And so if they tell you, okay, if they tell you that one of the factors in this exercise is z minus 3i, then you can immediately assume, so this is part of the parentheses. I'm sure there's a couple other parentheses going around, okay? But you know that one of them is these, okay, z minus 3i, which is kind of like saying, like, you know that one of them is x plus 1, okay? And so from here, you can immediately go ahead and say, okay, so this has to equal 0, which is the same process I did here in orange, right? And basically, well, technically, this guy here, see? It's the same process that you're doing right there. So z minus 3i equals 0, so you can immediately just say that z has to equal 3i. So guys, this is literally one of your roots, okay? And your other roots, and here's a big sort of trust me sort of energy. I'll try to explain it in a second, but really it's a trust me sort of energy. So if you have complex numbers and one of your factors, okay, one of your parentheses is z minus 3i, then the complex, the sorry, I got tricked up. Then conjugate, the complex conjugate is also a root, is also a root, okay? Massive information, you should be writing that down, okay? And so if one of the factors is z minus 3i, then the complex conjugate, because there is a z in there is a complex number going around, right? The complex conjugate is also a root. So if one of the roots was this guy here, then your other root is going to be z plus 3i equals 0. And so z has to equal negative 3i. This is your other root. Okay, so you can literally think about it this way. Your root 1 was this guy here. Your root 2 was that guy down there. Okay? Now, what the heck is a complex conjugate? How does that work? What is going on? See? So on the one hand, you have your formula booklet. Okay? And the formula booklet is very important that you get used to it because the day of the test, you will have 2 years of experience of this thing called IB. You will have probably 2 hours of sleep, a lot of study time done in your past, and a whole lot of energy for you to do well. Okay? And you will also have a pen and pencil, an eraser, maybe the graphing calculator depending on the test. And more importantly, and this is my point, the formula booklet. The formula booklet is a tool you can take in the day of the test, get familiar with it, know what's in it. A lot of it is useful and a lot of it is not, okay? And so for today's exercise, or for this exercise, better said, there is something very, very important that we have to use, okay? So down the line, we will be using this guy here, okay? Not yet, but this guy here. And for now, I wanted to talk a little bit about what is this, see? So here they tell us that complex numbers, okay, are z equals a plus bi. And all this is really telling you is that a complex number has a real part plus the imaginary part. Okay, this is a t. Plus the imaginary part, right? So the real part is the a, and the imaginary part is the bi, okay? And so if you were to sort of graph this, usually imaginary numbers get graphed as like vectors and stuff like that. See? So if you were to graph this, on the one hand you would have your real part, and on the other hand you would have the complex or the imaginary number part. See? And so basically you would have, say, here you have a, and over there you have your bi, and technically, okay, so this is like the OG, right? You can take this as the OG. And the complex conjugate, just so that we see it more visually, the complex conjugate, okay, is like, it's sort of like the mirror. It's like in the same sort of direction, but mirrored, right? And over here, you would have minus bi, okay? And so that is why if the OG is z equals a plus bi, then the complex conjugate is pretty much the same thing, just that you have z equals a minus bi. Okay, so the complex conjugate, you can think about it or memorize it or whatever you want, okay, as like the imaginary, okay, with times -1, okay? So if the OG was a plus bi, then the complex conjugate is a minus bi, see? And if you ever face an exercise where the original that they gave you was a minus bi, well, the complex conjugate is a plus bi, of course, right? Because you're going to be doing minus bi times -1, which gives you that positive bi that I mentioned earlier. All right, whatever. I don't want to go too deep into that. This is more of a visual aspect of what the complex conjugate is. Just recall that the complex conjugate is a -1 to the imaginary part of it, and it's also a root. Okay, that is the biggest sort of thing I really, really need you to understand. It's also a root. And so over here, I already found 2 roots. Okay, now you might be thinking, but dude, how many other roots are there? Like, this is crazy. Like, what's going on? And there's actually a fairly easy way to identify in polynomials what a root is. Okay? And so polynomials by itself is anything that is like, for example, this x squared. Actually, let me do it like this. So you have ax squared plus bx plus c. This is a quadratic. See, but it's a polynomial. It's a second degree polynomial. See, so it's second degree because you have x squared. If you happen to have something that goes ax cubed plus bx squared plus cx plus d, surprise, this is a third degree polynomial because you have a 3 up here. And the way to tell how many solutions, how many solutions you have is by identifying the polynomial grade that you have. All right. Now this is very fancy math definition. What I actually want you to remember or recall or write down is that biggest exponent equals amount of solutions. And so in this case, for example, we have an x to the power of 3. That means you have 3 roots, 3 solutions. Here you have an x squared. That means you have 2 solutions, right? Now we know because of the discriminant, some of them are imaginary, some of them are not, etc. Blah, blah, blah. Still, 2 solutions, 3 solutions, etc. Right? And so over here, what's your biggest exponent? Your biggest exponent is a 3. So, you need to find, okay? You need to find 3 roots. Right now I found 2, all right? So again, this is a very sort of context problem. I need to explain everything piece by piece. And now the next thing I have to explain is, okay, so you found 2 roots. Which one is my third? How can I do it? Blah, blah, blah. And this is when it's very useful to have tools in mind, okay? Technically, there's 2 approaches, all right? One of the approaches, which I'm not going to do, but I will show you the first step, is identifying that, okay, so if one of my factors is z minus 3i, and my other factor is z plus 3i, because this guy on the internet told me that it's a complex conjugate, then that means I have a third root going around, okay? That means I have a third root going around, and once I identify that one, right, and I can compare it to my original function, right, maybe I can find the last sort of root, okay? So one of the methods is literally just trying to like distribute backwards or figure out by intuition like what the last root should be, or factor out piece by piece from the original one until you end up with what the last parentheses should be. Okay, so that is one of the methods. I don't really want to get into it because I think the other method is a little more straightforward, but I do want to give you the tool in case you've seen it in class or whatever, etc. See? Anyways, the method that I'm going to show you has to do with the following. In your formula booklet, which I did mention that it's very important to get familiar with it, to learn it, etc., I gave you the foreshadowing, ooh, fancy word, foreshadowing, that this was going to be very useful. And so this over here is like a sort of math law, okay? And this is telling you that the sum and product of the roots of polynomial equations, okay, polynomial equations being like these guys here, see? Polynomial equations of the form blah, right? So basically that your polynomial, all this is really saying is that your polynomial equals 0. When your this is the thing, when your polynomial equals 0, the sum is this of the roots. The sum of roots is that, and the product of roots is that. So now we're getting somewhere. And so, well, what is this actually saying? Because here there is an a, there's an n. What is n? What is a? What the heck? Like, what is going on? See? First, let's go with intuition. So as I said, when your polynomial equals 0, there is a formula they can use for the sum of roots and also for the product of roots, which can be very, very useful in order to solve it. See? Now, piece by piece, what is n, what is r, what is happening? So, this n, which is the same as that n over there, and this n here, and all these other n's, okay? This n is your biggest exponent. And the a, which is appearing here, which is also appearing there, notice that a right here, it's next to what thing? It's next to an x. Ah, so the a is the constant. All right, now this is getting interesting, right? Because basically, what this is telling me, and notice, here you have n, so this is gonna be, you can basically think about it as like the constant next to the biggest exponent, while this one over there is a very similar idea, but it's the constant before the biggest exponent. All right. So basically, and if I actually apply that over here in this exercise there, see? So notice, when your polynomial equals 0, right, you have an equation that is basically telling you that the sum of your roots is going to equal the constant before the biggest exponent, which is what is on my numerator, divided by the constant next to the biggest exponent. Okay, so the sum of roots, we really need to understand this formula before we apply it to the big exercise. See, so using this simpler example here, the sum of roots equals negative a n minus 1. So this is the constant with like right before the one with the biggest exponent, divided by the constant next to the biggest exponent. See? So the sum of roots equals those two constants. See? So if I apply that here, well, the sum of my roots, we did say that the roots were negative 1 plus negative 3, right? This is negative 1, this is negative 3, equaling this one is, actually, let's do it the other way around. So first, the biggest exponent, right? So the constant next to the biggest exponent is just going to be negative because of this negative here, see? So the constant of the biggest exponent, well, what's my biggest exponent? It is the x squared. So next to the x squared, which is my biggest exponent, you have a 1. So on the bottom, you put a 1. And then right after the x squared, you have an x to the power of 1. So over here, you can put 4. So, so the sum of roots is going to be negative 1 minus 3, right? Equaling negative 4 divided by 1. So negative 4 equals negative 4. Boom. So that formula actually works. Wow. The formula booklet can be really useful. Surprise! It's going to save you. It really will. And so this right here is massive, you guys. It is an incredible tool that you can apply and basically really focus on the example I gave you. Because it's very easy to get mixed up on the an minus 1, an, and all that stuff, and etc. Dude, all this is telling you is that sum of roots equals negative um, um, constant before biggest exponent divided, right, by the constant of the biggest exponent, right? And so let's just review that one more time. This an minus 1 was the constant before the biggest exponent, so it would be, well, before the biggest exponent here is the 4, right? And the constant of the biggest exponent was 1. So that is why you had 4 divided by 1. You have a negative because that's what the, you know, the formula brings to you, right? And the sum of the roots is just going to be the negative 1 plus the negative 3. All right, so this formula is huge. I had to explain it piece by piece because I don't just want to throw it at you, okay? This is how it works. This is how you apply it. So now let's apply it to this super hard exercise, see? So if I try to apply it now, on the one hand, you know that you have 3 roots because you have z to the power of 3. And if you try to apply it now, well, you have the root, like the root of the first root plus the second root plus the third root, right, has to equal the second to last constant, right? and the biggest constant. And so the biggest constant here is just going to be -1. So you have negative divided by -1. And then the constant next to it is actually this. 36 divided by m. And if you go ahead and plug in the roots that you have, well, you can plug in the first one, which we said was 3i. You can plug in the second one, which we said was -3i, right? And then this third root, well, you still don't have it, right? But if you go ahead and try to solve this now, well, this goes away with this. You have your third root that you're going to discover soon. And here on the right side, you end up with negative 36 divided by m divided by -1. Which, first of all, looks kind of nasty, but second of all, you can't solve it yet because you don't have m. And so this is the next big step that we have to go through. Well, what is m? How can I find m? What can I do? How can I get m alone? And so the big step you have to do now is that in order to find m, what you can do, right, is that because you know, for example, that z equals 3i, that 3i is indeed a root, then that means that you can plug in 3i into your equation, and this must equal 0. You can also do it with the one on the bottom, right? You can also say that -3i has to equal 0. They're both going to work. So both of these are an approach in order to find m. I'm going to choose the one up top because I want to, but they both work, okay? Now, why would this help you find m? Because if you plug that in to your equation or formula or whatever, actually first let me write it down here. So it's your OG is 4m minus mz plus 36 divided by mz times z squared minus z cubed. So if you go ahead and plug in 3i here, first of all, it's going to look really nasty. And so what you're going to end up with is with 4m minus 3im plus 36 divided by m times 3i squared minus 3i cubed. And so yes, this looks pretty terrifying, but there is something interesting that just happened. So in the original one, which I am now putting in pink, so in the original one, how many variables did you have? Technically, you had the variable m and you had the variable z. So you had two variables, which is annoying. But now that you plugged in 3i, how many variables do you have? You actually only have m. And I know some of you might already be thinking, dude, what? What are you saying? I don't believe you. I don't believe you because there's an I going around. And I will say, yes, there is an I going around, but careful. I has a value associated to it. And so I is an imaginary number. That is why we're talking about complex numbers in the first place. And so I, ladies and gentlemen, is basically, or is, better said, square root of -1. And so the reason imaginary numbers exist in the first place is because if you ever, for example, say you have square root of 4, right? You're going to tell me, the solution of square root of 4 has to be plus or minus 2. Because you can do 2 times 2, and that gives you 4. Or you can do -2 times -2, and this also gives you 4. But if I go ahead and ask you, okay, now try to solve -4, square root -4, suddenly you can't answer 2 because, well, 2 times 2 gives +4, and -2 times -2 gives +4 again, right? And so there is no way to end up with a negative because you either multiply two positives or multiply two negatives. You never end up with a negative. And so the way to solve this would actually be to I, right? And so that is why the I exists in the first place. It helps you solve. This is the thing. Imaginary numbers. This is just like a useful fact. So imaginary numbers help you solve square roots that are negative. All right, that is like the big deal. That is why they were invented in the first place. Imaginary numbers help you solve square roots that are negative. See? So that is why they exist, and I equals square root of -1. Now, from there, because you don't have a calculator, you do have to try to manage these i's in the best way possible. See? And so from here, some of these i's, you can actually solve them like straight away, right? So on the one hand, because I equals square root of -1, then I squared has to be square root of -1 times square root of -1. So I squared has to equal, look at that, -1. I cubed is really just going to be -I. And I to the power of 4 is going to be +1. See? So these are things that are definitely worth keeping in mind. Everything that I'm putting in a box right now is very useful information. If you don't trust me, I get it. I'm a person on the internet. You shouldn't trust people on the internet. But this is a math video, so put your guard down. So if you put I into your calculator, I know this exercise doesn't allow calculators. I'm just showing you how I works. So I by itself just gives you I because whatever. See? I squared gives you that -1 I was talking about. I cubed gives you that -I was talking about. And I to the power of 4 gives you that 1. And you will actually notice, and this is just good to know, that this pattern repeats if you keep on going, right? And so to the power of 6 is the same as if it was to the power of 2. To the power of 7 is the same as if it was to the power of 3 because it's a pattern. Well, that looks kind of whack, but point is, it's going to start repeating. See? Here, the calculator just kind of loses it, but really I to the power of 8 is the same as I to the power of 4. That's what I was really trying to show you. I did not think the calculator would go kind of crazy there. Whatever, okay? I don't want to stray too much from the point that I'm already trying to make. So, enough blah blah. Point is, from here, you can actually solve I squared immediately, see? And so from here, you can go ahead and simplify what you can. On the one hand, you end up with 4m minus 3im plus 36 divided by m times, here this squared affects the 3 and affects the I, so you end up with 9i squared. Interesting. And over here, this 3 affects both, so you end up with minus, okay, you end up with minus 3 times 3 is 9, times 3 is 27, so minus 27 I cubed. All right? So, okay. Now it looks like we're getting somewhere, aren't we? So, from here, the context I mentioned a million years ago, we did say that the imaginary numbers that we deal with have a real part and an imaginary part. And so because we we did say that this whole thing equals 0, you have an equals 0 here, right? Then that means for this to be true, the real part has to equal 0 and the imaginary part also has to equal 0. And so if you divide it between imaginary part and real part, we'll first solve the I squared, right? And so the I squared is a real number, right? We did say that I squared was -1. So from here, you can end up with 4m minus 3im plus 36 times 9, which if you take your time and do it, I know it's without a calculator, so you're going to have to do it yourself, but 36 times 9, I think was 324. There it is. So 324, so you end up with plus 324 times I squared divided by m. Now, I squared we did say was -1, so really, over here, it just turns into minus 324, right? And this last number ends up as 27I cubed. Now, as I said, the real part has to equal 0, the imaginary part has to equal 0, so the real part is going to be, 4m minus 324 divided by m. This has to equal 0. And on the other hand, the imaginary part has to be 3im minus 27I cubed has to equal 0. So, now that I have the real part and the imaginary part next to each other, to solve the real part, which is a lot more straightforward because I only have m's going around. On the other hand, I still have i's going around, which are annoying, right? So I and m. For solving the real part, you gotta get m alone. Now, because you have m on a denominator, I strongly suggest that you just multiply everything by m. So if you multiply everything by m, you end up with 4m, right? So 4m squared minus 324. equals 0. So getting m alone, you do plus 324 plus 324, you end up with 4m squared equals 324. Divide by 4, divide by 4. M squared equals 81. You can trust me on that. You can double check later. So from here, you can now do square roots in order to get m alone. So m has to equal plus or minus 9. Now, is it positive 9? Is it negative 9? Technically, you can check by plugging it into the imaginary part, and whatever makes it make sense, you're good to go. But what I'd like to remember you, or remind you, better not remember you, what I'd like to remind you is that up here, way earlier, you did say that m pertains to the set of real numbers which are positive. And so, bada bim, bada boom, you can immediately say that m has to equal 9. So, guys, that was a very long sort of approach. I think this video is a little bit long, but it does go over pretty much everything you need to know for imaginary numbers. So, I think it has a good side. See? Anyways, all of that thing was just to find m, which we just did. So m equals 9. We concluded that m equals positive 9 because they did tell us that m pertains to the real numbers which are positive. Okay? If we weren't sure whether it was positive or negative, you would plug it into the imaginary numbers set here, and whatever makes it equal 0 is, the value of m that we will use. Anyways, so now that you have your value of m, we can come back to this part right there. So, this is what we were going for in the first place. We were trying to do the sum of roots, and it almost worked, just that we had an m going around. See? And so now that you can plug in now that you can plug in 9 for m, we can solve for the last root and be done with this very exciting exercise. And so your last root is going to be negative 36 divided by 9 divided by negative 1. Now, on the one hand, because you have a divided by negative 1, really what that ends up happening is that you end up with a negative times a negative, so this guy times this guy, and it ends up being that the whole thing is positive. See? So you end up with positive 36 divided by 9. So your last root has to be 36 divided by 9, which is 4. And so, boom, look at that. So your first root, just to be very organized, is 3i. Your second root is negative 3i because of the complex conjugate, and your last root has to equal 4. So ladies and gentlemen, that is how you solve number 7. It's pretty wild, and let me just make a quick recap of the approach we did just so that we really understand the process, because that is the main idea, right? Once you internalize all these different methods and processes that you can do, then that is an additional tool that you can use the day of the test. So basically what happened is that they gave us a factor. See? So because they gave us a factor, that immediately gives you two solutions, right? You get one solution just by plugging your factor equal to 0, which is the same stuff that you've always done, right? So you take that factor and you equal it to 0. That gives you one root. The other root arises because of the complex conjugate. The complex conjugate is also a root always. Okay, so you go ahead and do the complex conjugate. Basically, you go from negative 3i to a positive 3i. That is the only change you need to do. You only affect the imaginary part of your number. So once you do that, you got the other root, right? Now for the last root, and first of all, you know there's a last root because you have z to the power of 3. And so if it's to the power of 3, you have 3 roots. If it was to the power of 4, you have 4 roots. If it's to the power of 8, you have 8 roots. Because the biggest exponent tells you the amount of solutions. Now, you're thinking solutions, you're thinking roots, you're thinking factors, all these different things. And it should come to mind once you study enough with it, with the formula booklet, that there is a formula for a polynomial for the sum of roots. And so basically, all this stuff that is written here is just the fanciest way possible to tell you, yo, you have a formula that when your polynomial equals 0, you can basically take all the roots, sum them up, so the sum of roots is going to equal two constants, right? The constant of the biggest exponent on the bottom and the constant of the next biggest exponent on top. See? And I did a quick example showing it over here. So the biggest exponent was x squared, so you put 1 on the bottom, and the next biggest exponent is x to the power of 1, so you put the 4 on top. See? And so you take the sum of roots, which you said was -1 and -3, and we showed that the formula worked, right? And so because the formula worked, and we gave this very intuitive example, well, now you got to apply it for the polynomial with imaginary numbers at the HL level, which is absolutely crazy, but you follow the procedure, you trust the procedure, you trust this guy on the internet, not all of them, just this math guy talking about stuff. And boom, you found out this equation, and the only thing you were missing was m. And so how do you find m? Well, you plug in 3i into your formula, right? You plug in 3i into your formula, and we passed from having the variables of m and z to having only the variables of m, right? I is not a variable because we also talked about how I is a number. See? You found m, you completed the sort of like plug-in formula thingy majingy, and everything worked out nice and dandy. So, you guys, number 7 is pretty crazy. This video is probably pretty long as well, but I'm sure it helped out at least one of you out there. So this one's for you. I hope it helped, and I'll see you around.